Lightning and electromagnetic interference or lightning protection module 6.4. So, here we look at some principles involved or some aspects of communication towers protection, or it could be wind turbine protection also. And we will end this chapter with a cartoon on lightning safety. Previously, we have introduced upward lightning from tall structures, and upward lightning from tall structures are more and more prevalent when 4G or 5G communication towers are coming up and several wind turbines are coming up, tall wind turbines. Say for example, wind turbines of 5 megawatt can have heights of the order of 200 meter up to the rotor tip. So, you may have more incidents of upward lightning from these towers than downward lightning. So, there are some empirical observations of what is the percentage of upward lightning from a tall objects compared to the downward lightning. So, this is provided by Ericsson in 1978. So, the empirical relationship states that the percentage of upward flashes from a wind turbine or in those times high tower, there were not that many wind turbines then. It is given by 68.2 log of HS, which is the height of the object, minus 315.5. So, this is an empirically empirical relationship derived from many observations. So, what it means is that if a tower is of around 450 meter or high, there are several towers around the world now, almost all flashes to that tower are of upward flashes. And if it is height of around 200 meter on level ground, around half of all flashes will be upward flashes. And below towers, below heights less than 100 meter, you do not have many upward flashes, mostly it is downward flashes. Now, there are exceptions to it, because if you have a tall mountain and even a tower of 10 meter or 20 meter can produce lot of upward flashes. That is mainly because of the field intensification caused by the mountain itself. Some aspects of lightning protection. Wind turbine blades are the most expensive object damaged by lightning protection and the most difficult to replace also, because transporting a turbine blade is an enormous task and downtime will be quite large with a wind turbine blade breakdown. So, lightning can strike blades even without any metallic components in it. Because it need not be metal. If it is a tall object, that object will intensify the electric field around it, because it may be wet or something, and lightning can strike that object. So, there is often a misconception that okay, since the blades are not conducting, it will not be struck. So, that is not the case. Blades are hollow structures made of composite materials such as glass, reinforced plastic, wood and carbon reinforced plastic. And because of this hollow structure, most severe damage to blades is caused when lightning forms arc inside the blade, because then you create a very strong pressure shock wave and the whole blade can explode into small parts and caused injuries to people nearby or objects nearby. So the lightning protection of blades involves safe conduction of the lightning current away from the blade, so that it is not allowed to form any arc and safely to earth. So it is almost like building protections, except that blades are rotating, so you need to take care of the connection from the blade to the rotating hub, then from there to the earth. And you need some special consideration in blade protection also, that we will see in a moment. So these are some of the possible designs used in blade protection. This is adapted from the IEC standard 61400-24, which is describing about protection of wind turbines from lightning. One of the main considerations is that installation of down conductor along the blades should not affect the aerodynamic properties of the blades. That is very important. And here in this example, this is a small lightning terminal. Then you have a down conductor system. So most likely lightning will attach to this small terminal over here at the tip of the blade. And this is a metallic wire inside the blade. Now another example is that along the edge of the blade you have metallic wire embedded or on the surface of the leading and trailing edge of the blade. So here you have a strip, a metallic mesh or mesh on surface under the gel coat of the blade. So there are several blade designs. So in tower protections, what are the important? So wind turbine is also a tower. So after the blade, then basically the rest is like a tower. Then lightning current is coming down. So what are the issues involved in that? Say, you might have seen several paper reports when a 5G or 4G tower or 3G, even 3G towers are coming in a neighborhood. The mobile operator has installed the tower, connected everything. Then houses around that tower complains about damaged TV and other equipments during lightning storms, whereas they never faced those problems before. So part of the reasons for these things are not enough protection, lightning protection for those towers, or not enough integrated lightning protection. So we will see why and what are the problems involved and how those things can be prevented. So the basic problem is like this. So you have some tower, then you have a building that houses equipments to that tower. Sometimes this building may not be there, instead it will be just a box in the tower itself. Then you have the local network, power network, because the tower may be powered by the common transformer connecting to the local network. So there is a local connections to the tower. So often what happens could be that lightning is striking the tower, then from there some part of the current may be going to the ground, but the other part of the lightning current may go to the transformer, and from there it get into the power cables to the local community network and enter into the buildings as conducted transients. So lightning is striking the tower, then as conducted transients it is getting distributed to the local network. This may be what could be happening when people are complaining about damaged TVs and equipments after the tower has come up. So, there is a huge potential rise at the tower building complex during lightning strike, and this may drive currents via cable shields to local power network. So, for protection, so this is one schematic diagram. So, for example, what tower operators could provide is that they have to provide very good lightning protection. Mainly, it is not enough to install their equipments at the tower by installing such protectors and all. They need to dissipate most of the lightning current to the ground. So, often towers are placed in rocky grounds or in small hilltops and all. So, you will not be able to provide deep ground rods very often. So, even if you do not have, it is not possible to provide vertical ground rods. Instead of vertical ground rods, or in addition to that, you can provide ring conductor and horizontal buried radial conductors as lightning earthing system that can dissipate lot of lightning currents. Then if you have a electronics housed in a separate building, you need to bond those buildings together by earth conductor, and the building also require ring conductors, and its equipotential systems are connected to those. Then you have the service cables going into the building. Its shields are connected to the equipotential bar. In addition, you can provide a buried earth conductor that is traveling along the service cables, but this has to be buried. It is not enough if it is just lying on a trench isolated. So, this has to be buried in the soil, in touch with the soil. So, this follow on earth conductors, this is buried in soil. So, this is a bare conductor also. So, then this follow on earth conductor will take a large portion of the current and dissipate into the ground, and the current on the cable shield will be very small. So, that will save the local community network from lightning related surges even when the tower is struck by lightning. Now, this can be shown by this simulation. This is actually a simulation illustrating the principle. Suppose you have a buried cable. So, in this case this particular cable is around say 500 meter cable. In the simulation it is terminated into 50 ohm at both places, and this is 10 ohm that represents the local community network roughly. Then you have the possibility of connection between the shield and the earth conductor. So, this is in microsecond. So, here a current source is connected with a fast impulse of 0.1 microsecond by 50 microsecond. 50 microsecond is the fault time. So, an impulse current like this is given. Then say you gave kind of 1 ampere current, then you can extrapolate it to say 1000 ampere or something like that by multiplying the result by 1000. So, the first curve, this is what is shown. The curve shows the potential difference between the cable core and cable shield at load N. So, this voltage V is shown here between the core and the shield at the far end of this 500 meter. So, the first thick curve what is shown here is without follow on earth wire. So, this is the follow on earth wire, and the dotted curve is shown with follow on earth wire connected to shield at injection point over here. So, you can see that when this wire is connected, these voltages appearing here, the differential mode voltages appearing over here due to the transfer impedance of the cable, due to the current flow along the cable is reduced very much. So, the curves represent the voltage appearing between the inner conductor and the shield at the other end. So, the thick line shows without the follow on earth wire. So, if you have just a cable, and this is the case mostly normally when towers are erected, very rarely people put this bare conductor. Now, if a bare conductor is buried in soil and connected at this end of the cable shield, one can reduce the induced voltage at the other end drastically, and that is shown over here. So, this is a very effective strategy in reducing the transfer of lightning energy to the local network. So, this 10 ohms impedance roughly represents the local network. Now, one can come to lightning safety. So, this lightning safety is described or presented here in the form of a cartoon. This cartoon was produced by a European Union project that we were all involved about 15 years ago. So, it shows two cartoon characters Siggy and Sack talking about what to do during lightning, whether you are at home or in town or in a park outside. And the terms used here are not really scientific terms, but in terms of the layman, so that people can understand that. So, but it shows generally the principles to be adopted during lightning strike, so that personal safety can be safeguarded. Say at home, so it is a bad idea to go out, a thunderstorm is coming. Yeah, that is true. If you see a thunderstorm coming, better to keep yourself at home, especially if your home is a normal proper structure, concrete building, because that offers some protection. But if it is a small hut, well, it does not make much of a difference whether you are inside a small tent without lightning protection or you are outside. But a proper brick or concrete structure, even without lightning protection, offers some protection. The weather looks fine to me. Remember that the thunderclouds can move closer and strike surprisingly fast. That is true, because even though sometimes you have this convective storms that comes from, you have storms, frontal storms that come from one side to your town and pass the town like that. So, this part may be very clear, sunny, and but the thunderstorm is approaching, and very fast you will be in the middle of a thunderstorm. So, you have to really watch out. do not go outside and stay away from all electrical appliances. So, this is what you can do when there is a thunderstorm outside. You do not want to be close to electrical appliances because those appliances are connected to the electrical lines. It could be that lightning may strike somewhere else and something can get into the electrical network, and that may have, and if you come close to it or touch it, you may get an electrical shock because of that transient lightning. It has been 30 minutes since the last flash and thunder. Yeah, it is safe to go outside. So, you really have to wait out the thunderstorm to be out again. So, this is if you want to be absolutely safe. Then if you are caught in thunderstorm while you are in the town, you can determine how close the thunderstorm is. So, that can be done by counting the seconds between the flash and the thunder. Remember that the sound travels at speed of around 300 meters per second, whereas lightning is almost instantaneous, 3 into 10 to the power of 8 meters per second, and both thunder and lightning flash are produced simultaneously. So, you will first see the lightning, then when you start counting, approximately you can take that if you count up to 3, it is 1 kilometer, 6 seconds means that 2 kilometer, like that you can count. So, you can see that from the number of seconds divided by 3, you can see that how far lightning is away. So, 30 seconds means that okay, lightning is approximately 10 kilometer away. So, it is approaching close. So, you need to look for a shelter because it takes some time to find a shelter. So, you do not want to stay close to a car because that is a metallic body. No, it can produce upwards, I mean it can, lightning may strike it. Or you do not want to be close to a building standing outside because building may be struck by lightning. But if you are inside a car or inside a building, that is the safest places to be, because inside the car you are almost like a Faraday cage. It does not matter you have a tire, rubber tire and all. If a flash can come through insulating air all this way from the cloud, it is no problem for it to break down across the tire. So, if you are inside a car, that is quite safe, but then try to keep away from the steering and other metallic parts of the car if possible, because in case the car is struck, you do not want any of those currents to get into you. But you can use a mobile phone and call people. So, if you want to make any call, use mobile phone, not the landline. Mobile phones are safe because you do not have any physical connection to that. You may have crackling noises and all, but that is not dangerous. Now, if you are at the park then or outside, you need to find a safe place. It is dangerous to be close to big towers and all, because very likely those towers may be struck by lightning, and you can have, and if it is struck by lightning or I would not say most likely, there is a possibility that towers can be struck by lightning, and in case it is struck by lightning, you can have very large radial currents, and these radial currents can produce a lot of step potential which can electrocute people. So, that is why you have to keep away from these tall objects and tall towers, and you do not want to be in the water, because if you can be electrocuted if anywhere in the water is struck. Water is a fairly good conductor, and that is not good. So, you have to be out of the water, and you do not want to be on top of a hill or near to a fence or on isolated clumps of trees either, because that when lightning can strike any part of the fence, you can get a arcing to you, or hill is a prominent place, protruding place, so you can be struck by lightning, and clumps of trees are also like that. Whereas, if you are in the middle of a forest, everywhere it is tall trees and all, that is much better. You are not sticking out. The principle is not to stick out. So, that is the same principle being when you say that, okay, do not have your race umbrella like that because you do not want to stick out too much. The best position to be is if you can't take a shelter, be in a crouching position like that if possible, so that you are not sticking out. Then you keep a distance from the other persons. Do not crowd together, because even if one person is stuck, it is not affecting the other person. So, direct lightning strikes are rare events, but still lot of people are getting killed by lightning. Not always direct, but somewhat indirect, in the sense that it may be striking a fence, or it may be striking a tree nearby, or then you get caught with it. Trams are safe if you are inside the tram or inside a bus or something like that, but because trams are connected with lines or trains, and anywhere lightning striking anywhere can affect the train. But when you are stepping, but since it is like a metallic body, you are safe, a Faraday cage, but when you are stepping out or in, you may be in danger because of the large potential differences. So, that you need to avoid during a thunderstorm. So, these are some of the principles to be used. Well, sailboat is very dangerous because of the tall mast and all. So, this cartoon is produced by the COST P18 action of the European Union, where several groups of lightning researchers were exchanging ideas and conducting joint research projects. So, for the public information, this brochure was produced, which was translated into several languages. So, that is something about lightning safety. So, this will end the chapter over here. Thank you.